Hello there. Today we're going to be implementing and talking about the concept of an array-backed list in C. Alright, I made myself a little bit smaller for the drawing part, so hopefully we can see everything that's happening. To understand why you'd want to use an array-backed list versus something like a linked list, you have to understand a little bit about how memory works. When you declare an array, then the order of the items in your array is guaranteed to be one after another in memory. That means if you want to get this 6, for instance, you can get the pointer to the first element of the array, which is usually just the array variable that you declared, and then you can add, using pointer arithmetic, 0, 1, 2, 3. So array plus 3 equals 6, or rather the value inside array plus 3 equals 6. Now that's the same as saying array with the square brackets 3. This is a shorthand notation for this, basically. So what does that mean? That means if you want to get from the start of the list to the end of the list, it's going to take however long the list is. So that's the same for arrays and for linked lists. That's no different. But if you just want to look something up and you know that it's stored in this position 3, then the time to look that up is 1. So the time to look up this element, number 3, or the fourth element in the array, or rather it is the 5th element, but the index 4, which is the number 5, it's the same. If you add a million things to this array and then you look up the 500,000th item by saying array 500,000, then it'll be exactly the same. It'll take the same amount of time, rather. However, with the linked list, you have something like this. This is the same data, but we're going to express it as a linked list. So a linked list is, if you don't know, pretty similar in the ways that you might use it. So you put a bunch of data in the list, and the difference is you have the data, and then you have another piece of information right next to that data, which is a pointer, which points to the next piece in the list. So because linked lists work this way, they have a particular ease of use. If you want to remove the 7, you just remove the 7, but make sure you save a reference to the 6, and then you grab the 2 and you say, oh, actually the next one of this is the 6, and that's it. That's all you have to do. But with an array, if you want to remove the 7, well, you can't just remove this. You have to make a new array which is shorter, copy these values into the start of the array, and then copy these values into the remaining space so that you have a shorter array. Now, if you want to do that every time you add or remove things from an array, it can be pretty cumbersome. That's why you would make something like an array-backed list, which is what we're going to be going into shortly. Now, the advantages of arrays over linked lists are the fact that they are contiguous in memory, right? So because they are one after another, when you load an array from your memory to do something, let's say you have 10,000 somethings, balloons that you want to pop or whatever, right? You can load all 10,000 of them and then just go through one after another, and they'll all be loaded, most likely, assuming they can fit. But with a linked list, because the items are spread out and they could be anywhere in memory, so if you make this item A, and then way later you make another item B, I mean technically this is the first item and this is the second item, but there could be thousands or millions of other bytes in between those two. So you can't just go quickly between them. However, linked lists do have some advantages. One of them I just pointed out, which is the removing. Adding is also very easy. Arrays are fixed size, so you can't actually just add something to the end of an array. you have to create a new array and then make it larger, copy the contents of the old array into the new array, and then add the last element afterwards. This solution is going to solve these problems, or at least make them abstracted away from the programmer, i.e. the later version of you, if you're going to use the array backed list. Linked list performs pretty much the same in searches. So if you want to find something, like let's say you want to find this 6, and you don't know that it's at number 3, or at index 3 rather. With an array, you're going to have to go through one by one and find the value, and with a linked list, it's the same. However, there are other data structures that can make these kinds of processes easier. If you want to look into them, one of them is a binary search tree. Okay, now that we sort of understand what an array and a linked list are, what is an array backed list? We want to combine the simplicity of adding, removing, well, just adding and removing, basically, from a list. But we don't want to have to worry about resizing the array and copying the values and doing that every time. So we make a data structure, or rather, we make a set of functions that uses an array in the back end. We just say, okay, we want an array of elements. The size of the elements, let's just say they're 4 bytes each. Okay, and we don't know how many of them we want. We just say we want something with 4 bytes each. So it's going to start off actually with 1. You can change this to whatever you like, but in this instance, we'll start with 1. And then when we add something to it, it's going to check, okay, is the array full, basically? If the array is full, it's going to double it. Okay, so now suddenly we've got 2. Let's change this to 8. Right, and then we add another thing. Okay, now it's going to check and it's going to double it again. Okay, so now we go up to 12 and then 16. Okay, and now it's full again and it's going to double it again. Okay, you see where this is going? So the reason that we do this is because over time, this should average out to being a linear operation. But you know, it is possible that you add this many things and then you add one more thing, right? So it's 20 bytes and then this is unused and then you've got wasted space. So that is a downside to this implementation, which you should be aware of. There is potential to have wasted space here. Whereas if you did all the management yourself, or you change the implementation to only increase it by a size of 1, then there would be no wasted space. But the downside is, every time you add to it, if you only increase this by 1, every time you add, you have to copy all the values. So there's trade-offs either way. Alright, in this example, I'm actually just going to make a main file here. And then we'll write the function definitions at the top, and then we'll write the function implementation afterwards. Alright, so we know we want a list of some kind, so we'll make that a struct. And we know that we want to keep track of a few pieces of information. First of all, we want to know how many things are in the list, and then see, well, when you're making a data structure, you're going to have to keep track of that stuff yourself. We want to know how many things we can put in the list, because we know that the list doubles every time we don't have enough space. So it's possible that there's going to be some empty elements at the end. And we want to know how large the things are that we're putting in the array. So we'll put an item size. And then we want the actual array, which we're going to use void pointers for, so that we can put anything in there. So it's not a list of integers, not a list of character arrays or strings. It's not a list of any particular data type. You can put whatever you want in there. Okay, so that's that. We're going to have to include a header file for the size t type here. What else do we want to do? We know we want to add to the list. So we'll do something like this. The reason that we're returning a void pointer is because usually when you add something to the list, you want to return the item that you just added as well. Alright, so we've got the reference to the list and then a reference to the item. The data is going to be copied into the array. So even though you're referencing an item, once it's copied into the array, Those are two separate things. So you're not actually moving it, you're copying it. Just to be clear. Now we know we want to add things, we also want to remove things. So let's do that. We'll do a list rm. We need a reference to the list, of course. And then we need an item to find. So this is removing by searching for the item. Alright, slight wardrobe change. It's cold, but not that cold. Cool. Now what else do we need? We need a way to create a list. So let's make a function for that. Parameter, because we need to know what size the elements are going to be. And then it's not going to return void, actually. It's going to return a struct list pointer. So rather than the programmer having to make the struct list and then pass that in here, we're just going to return it back to them. And what else do we need? We need a way to destroy the list. So we'll make another function here called list free. Okay, so these are the functions that we're going to focus on. Okay, despite the order, I'm actually going to create the new function first because we can't do anything until we have a list. Now, we're actually going to allocate this on the heap. So when we run the list free function, or when we write it, we need to make sure that we free this correctly. Okay, there we go. Pretty simple. Now we want to make sure that we zero out all the information here and just set what we need. So we need the eye size. And everything else we're going to set to 0 or null. And the items we're just going to set to null for now, because there's no point allocating memory when we don't have anything to store yet. You know, I think I should write the free function now because it's very simple. This is another beauty of using an array-backed list. This part is insanely easy. So we just want to check if we have more than 0 elements, which means we've added something. Then we free the items, which is just an array, so we can just free it like this. Not array, items. Okay, and then we just free the actual structure itself. That's it. As simple as that. Now we've got creating a list, destroying a list. We should add to the list. Let's do that. Okay, this is definitely going to be the most complicated function, and as such it will require a bit more explanation. So I'm going to write this out and then we'll go through it. Okay, the first case here is if we have nothing in the list. So if there's no items in the list at all, then all we're going to do is allocate size for something, which is of the size I size, then set the maximum amount to 1. So the count is still 0, but the max is 1. The next case that we're going to check for is if the count and the max are the same, that means the array is full. So we need to double the size. So let's write that out now. Okay, so the first expression here, we're just getting the size of the elements, getting the amount of space that we have, which is this max, then we're just timesing it by 2. Now we're reallocating the entire array to this new size, and reallocate also copies the data, so we don't have to do that manually. Now we want to check to make sure that this realloc worked, and if it did not work, we're going to exit the program. Okay, now we just want to set the list of items to the new array, because it's possible that the pointer moved. When realloc reallocates the memory and copies the data, it might be in the same place, but it might not have had enough space to extend it, so it might have moved it somewhere else. So now we need to make sure we set the pointer to the start of the array to that new position. And then of course we need to multiply the amount of space that we have by 2. There's something missing from here, which is actually adding the item, and that's what we're going to be doing next. So we're going to be using this technique. I don't know if there's a name for it, but if you know that you need to add data to a particular byte in memory, let's say you've got an array of 4 integers. Okay, every integer is generally speaking 4 bytes. Okay, and you want to add something to the third one, but for some reason maybe you don't know it's integers, or you don't know something. For some reason you can't just use the int casting. And what you can do is you can get a character pointer, and then you can move it n bytes along the memory until you get to the position that you want to insert, and then you can use that pointer to copy data into it. So I'm going to show you how to do that, and that's what this POS or pos position, that's what this is for. So let's have a look at that. So now we're going to set the position to the point in this array where the first empty slot is, which is essentially the end for our purposes, the end of the list. Okay, so that's what this is doing. Now, we're going to try to copy the item that we've been given by this function into that spot of memory. And if it fails, we're going to exit the program as well. Memcopy is pretty interesting. So the first argument that it takes is the point in memory that you want to copy to. The second is the point in memory that you want to copy from. So, and the third is the size. So if you want to copy like an integer, well, you can just assign it in C. But if you want to copy some other data type, C doesn't have a type for it, you can use this and a void pointer to copy X amount of bytes from A to B. So it's pretty cool. And the last thing we want to do is just increase the count because we've added a new item, and return a pointer to the position in the array where the item was added. So we're just going to return position, if I can type it. Cool. So now we can create a list and add to a list. We are missing a couple of includes here. We're going to need... I would like to install a language server. I should do that. Alright, that should be enough, I think. Cool. So, let's actually write the main function. See if we can test some of this stuff out. So we got a list. Now, we're just going to store integers to make it a bit easier on ourselves. So we've got the list. Now we want to add to the list. So we have to pass a reference to the list. In this case, since it's a pointer, we don't have to use the ampersand because it's already a pointer. So list, and then what do we want to add? Well, we want to add a number, but we don't have a reference to a number, so we're going to have to make one. So we just say A is 23. Let me just move this up to the middle. There we go. So A is 23. So we just want to pass a reference like this. We don't have any way of seeing this data. So all we can really do is just make sure that it runs. I generally like to use a few options when I'm compiling. I like to use C89 standard because it's the most portable, and also I'm a bit of a hipster. I like to use G3 so that you can actually debug things properly. And I like to use W error, which turns all warnings into errors. So let's just hope that I didn't mess everything up. And I did. There's a couple of errors here. First of all, I did not include string.h, which we need for memcopy. Still getting used to this callback thing. Alright, string. And then line 52. We've got a problem here. I didn't even put an equal sign. Alright, there we go. Compiles. And if we run it, cool, it runs. But we can't actually see anything happening. So, okay, I've set up the debugger. We're running to main. Now we can see we've got this list here. Can you see that? I'm going to try and zoom in a little bit. Where is it? There we go. That's better. Nice and huge for my old eyeballs. Alright. So we're going to add list here. It's currently got nothing. And it's got nothing, nothing, nothing. We need to actually add a... Can I add a breakpoint here? Continue. Yeah, cool. So now we can see that items, well, it has something in here, but we can't see what that is. Unless I'm just being obtuse, and that's 23, but I'm pretty sure it's just a pointer. Well, we can see that we've added something. The eye size is correct, the max is correct, the count is correct. So let's see if we can print it out, because we know it's an int, right? Oh yes. You need to declare variables first before you can use them. Okay, cool. No compile errors, and because I used eye size. That's not what I wanted. I wanted count. Alright. That should do it. Let me add a break here. There we go. Alright, so we've added 23, and we can see index 0 is 23. Now, let's add something else. Okay, so somehow my semicolons got removed there. We're gonna change this to 42, and this can be 53 or something like that. And we need to actually change the variables because that's going to be a problem. Okay, now add A, B, and C. Of course, this example is rather simplistic. Like, if you're just going to be adding numbers to a list like this, then you'd want to just actually use an array. Alright, so that is incorrect because I did the pointer arithmetic here wrong, and this is supposed to be... Let's try that again. There we go. That's what we were looking for. So I just put the parentheses in the wrong places. Very cool. So we can add things from the list. That's great. Now, this was the most difficult function, and it wasn't that difficult. So why don't we go through how to remove something. Let's type that out. Actually, I'm going to go up here and grab this. Alright, so when it comes to removing something from an array, there's a few ways you can do it. You can make a new array with one less element, and then copy the first segment, or copy, and then let's say we want to remove this 6, for instance, right? So we copy this segment, and then we copy this segment here, so these two, into a new array that's 4 long. That's not how we're going to do it. We're going to, instead, we're just going to say, okay, we're going to use the same memory. We're not going to copy the array. We're actually just going to grab everything after the 6 and shift it up 1, right? So we're going to end up with 2, 3, 4, 7, null, 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 null. Right, and this 6 is just going to be overridden by the 4. So we're going to actually keep the same address in memory. So this is going to be identical. The pointer here, the pointer here, it's still going to be the same address to the start of the array. Let's go into how you might do that in the code. Alright, firstly we know we're going to need to search through the elements. So we're going to have to stick an int I up in here. And we know we want to grab the position of the element that we found, if we find one. So we're going to use the character pointer trick again. So we're just going to set that to the head of the list, or the first element. We need to know how large the size is after the element that we found for the rest of the array, so that we can shift it all up 1. So we're going to call that tail size. Now we only want to loop through the items that are currently existing in the array. So you know how the array doubles in length, and sometimes the end of it will be empty. We don't want to go past the known values because there could be other data in there, depending on how you write this. There's also just no point going past, so we'll just go up to the count, which is the current amount of items. Now we're going to use something here called mem CMP, or memcompare. This is really cool. So this is a way, and I'll explain that 0 in a second. This is a way to basically say, okay, is this set of bytes exactly the same as this other set of bytes, like the content inside them? So, you know, it could be totally different positions on the computer, but you've got the number 23 here and the number 23 there, but you don't know the integers you can say, hey, are these bytes the same values as these bytes? And if the answer is yes, then this will return 0, which is a common thing that can definitely trip you up if you don't know it in C. A lot of the functions will return 0 if they're successful, which just means no error, or it means success. But if you write this if statement and you remove this 0, you just say, okay, if mem cmp, and then we're going to do position, item, and then the size, which is the I size that we have in our list struct. You'd think in other programming languages this kind of stuff is common and this would just return true, right? But the standard in a lot of C is to return 0 if there's no problem, basically. So that's why we do this. So now we want to calculate the tail size. So we've found an item. We want to say, okay, what's the size of the remaining items? So we can use that in a calculation in a second. So we're going to get the max number of items. And we're just going to subtract, if I can find the right symbol, we're just going to subtract the position that we found it plus 1. So that'll always give us the remaining items. Then we're going to times this by the size, because we don't actually need the index, we need the size. Now we're going to use memcopy once again. Memcopy, and we're going to be copying into the position that we found. So like I showed you in the diagram, we're just going to move everything up. So we're going to copy from there and paste it on top of the one that we're deleting. So this is the position we found, and then we're going to get the position of the next item, which is just, this is pointer arithmetic, so it's saying the position and then plus the size of whatever it is, so plus that in memory, and then we just copy the tail size. Now if this is null, then something has gone wrong and we're just going to exit the program. Not success, failure. There we go. Now we have to actually remove or reduce the count as well. So when we remove an item, we want to make sure we reduce the count, and then we want to break out of this loop, because if we don't break out of the loop, it's going to keep going through the list and continue this process, which is not what we're looking for. And then here we just want to actually shift the pointer position every time we run through this loop. That should do it. We've got errors again. Right. I forgot to put an equal sign here. Wow. Okay, there we go. Cool. We've got these three things in the list. 23, 42, 53. Let's use this example. 2, 3, 6, 4, 7, right? 2, 3, 6, 4, 7. Cool. We want to remove this 6, right? Actually, I'm going to break this out into a function. Nope, it does not, because I forgot to copy the I over there. There we go. That's what we wanted. Alright, so we're printing the correct numbers. Now, let's try removing one. We can see that has worked, but it's a bit annoying. So I'm going to add something at the end here. There we go. Cool. Now, if this is working as expected, let's jump over to the debugger here. We'll start this again. Okay, we'll go to main. Now let's go down to here. Actually, let's stop here. Let's stop at each of these. So we're going to continue. Now keep an eye on this max and count. So continue 0, 0, nothing's been added yet, but after this function, we've got a count of 1 and a max of 1. Nice. Now if we go next, we should see the max double. There we go, max of 2 and a count of 2. Now the next is the first time we should have a different value here. There we go. Count of 3, but a max of 4 because it's doubled again. Now if we go continue again, we've got a count of 4 and a max of 4. And let's just go one last time, and it should go to count of 5, max of 8, which gives us the empty values like we saw here. We'll go past this, so we're going to remove from the list now. And you should see the count go down, but the max will stay the same. There we go, counts down to 4, max is still 8. So, before we move on, let's just test to make sure that we can remove multiple things and then add things, and there we go. So 23647, that's correct. Now 2347, that's the same as before, we've removed the 6. Now we wanted to remove, what was it, the D as well, which is 4. Now it's 237, that's right. Now 23723, that's correct, we've added the A and B again to the end of the list. So it's working exactly as we would expect. That's awesome. Alright, thanks for watching. I hope you found this video informative. If you have any questions, make sure you leave them in the comments. I'll get back to you. Unless the question is, can we be friends? Because that's definitely a bot. Make sure to check in on Sunday for the next engine episode. If you missed the last one, I actually used this list, or something very similar to this list, in the episode on last Sunday, so make sure to check that out. In the next episode of the game engine, we're going to be working on the event loop. I mean, not the event loop, the game loop, using the event system. So that's going to be pretty cool. Make sure to check that out. I'll keep you guys updated. And next Wednesday, we're going to be doing another episode similar to this. I might get around to doing the binary search trees, but maybe not. Yeah, regardless, I will be sharing some knowledge with you all as much as I can. Alright, so thank you and catch you.